Ken Birman is the N. Rama Rao Professor of Computer Science at Cornell University. He focuses on high performance distributed and cloud computing. His current work emphasizes Cascade, which reduces the data movement overhead in AI and ML systems by running computations where data resides, often achieving large speedups over other platforms. Vortex extends Cascade to specialize in retrieval-augmented LLMs and approximate search vector databases. Both of them leverage Dutreco, which is an RDMA-based framework that accelerates data transfer and persists in modern storage. And it includes a collective communication library, outperforming traditional HPC solutions. Ken Birman's group also explores the edge computing for privacy-sensitive, bandwidth-heavy applications in healthcare and industrial settings. Previously, his software underpinned mission-critical systems, for example, at the New York Stock Exchange and in air traffic control systems, ensuring fault tolerance and consistency. So besides research, Ken Birman teaches systems programming.
Paul, we don't need that part.
All right, let's move on.
I should have interrupted on sentence 2 or something. So if I could share.
Go ahead.
If I can find my PowerPoint and share it. There it is. Okay, I made up a couple of slides. Let me explain the context here, Paul. First of all, I'm going to be an occasional participant in this, and I'm an occasional participant in Mulligan Stew too, the other thing Paul mentioned. I have a lot on my schedule, as I'm sure a lot of you guys do too. My specialty is atomicity and consistency, or at least that's been a focus of mine for my whole career, 45 years by now. Paul asked if I could lead a discussion on what it would mean for open atomic Ethernet to be atomic. And I agreed to do that. So today, I just have a couple of slides, and the idea is to get people to chip in and express their views. Okay, I put Paul on the front here, but he hasn't actually seen these slides, so he can disavow anything he wants. Let's talk for half a second about why atomicity and other related models are valuable. The other models might include transactions, state machine replication, various forms of synchronization for NUMA processors, for example. I would argue that fundamentally, the world we're in is one in which we want our hardware to run as rapidly as possible. And that often means asynchronously at many different layers, whether it's asynchronous pipelines of updates to DRAM memory at a cache line atomicity granularity, asynchronous transfers over a network where we don't wait for ACKs for every packet. There's been discussion around that on the WhatsApp group, for example, where people seem to assume that somehow open atomic Ethernet is going to have an ACK for every packet. And that's not really what we want to be doing. We want to be asking ourselves about the abstraction of atomicity or a guarantee. And then separately, we want to ask how to implement it. And open atomic Ethernet should offer the implementation primitives enabling various atomicity abstractions. So, hardware performs best when it's allowed to be asynchronous and often when it can reorder operations. Meanwhile, software performs best if it stalls as rarely as possible, if it has a minimal amount of additional barrier synchronization. And yet, we want this explanatory power. We want to be able to have concurrent higher level applications that are built over this new hardware layering to perceive a coherent explanation for the evolving system state, to maintain implicit agreement without having to separately exchange messages and so forth. So we're trying to extract a maximum amount of deductive power and essentially implied agreement from a minimal amount of delay in synchronization. And that leads to today's topic, which is only going to be a few slides, by the way. After that, I want to open for discussion, which is this question of what it means for OAE to be minimal in the sense that it is the enabler that has been, how you make a sculpture. Well, I can't sculpt, but if I did, by taking a block of stone or clay and then removing everything that shouldn't be part of the sculpture. Well, we have the same challenge here. We want the Open Atomic Ethernet to be minimal. It should have as little as possible and yet enable the widest possible range of synchronization abstractions. Because I don't want to say we mean atomic in the sense of an atomic exactly once RPC or a database transaction. I want to say that we mean all of those things. We mean anything that people might want to build, and we would expect them to build it, or perhaps a library builds these things on top of the hardware, and then people use that library. And the Ethernet chiplet shouldn't be doing higher level things, and yet it has to have enough functionality to achieve these goals of explanatory power at minimum delay. The focus then is going to be on building blocks, and our job in this discussion, and in a sense your job, because I'm seeing myself more as a consultant to the group than as the actual leader in the sense of driving a spec, should be to push towards something where you can't carve away any aspect of it and simplify it without violating one of our larger goals of performance or of efficiency, or the capability of implementing these higher level atomicity abstractions. Okay? So let me give an example, and I'll give the example of the system that Paul butchered the name of. So a derecho is a type of very violent storm that sometimes accompanies tornadoes. It's a sort of a straight line wind. You get it when two storm cells converge, and you get sometimes for many miles a sort of high-speed jet of air that can be 200 miles an hour, knocks over every single thing in the way. I know it's a violent image, and actually, if you've ever been anywhere near one of those, they're scary. We actually had one in Ithaca once, and it literally bulldozed every tree for about 20. I would go out biking and for years, see the path that it had cut, snapping the trees off if there was a little gully. So it's a violent image, but the reason I like it as an image is the idea that the higher level mechanisms we're building shouldn't get in the way of the blinding speed that we want these next generation networks to achieve, right? Now, derecho is a library that builds an atomic multicast. Everybody sees messages, fault tolerance guarantees, and they see them in the same order if they overlap. And Paxos, which is a slightly stronger guarantee, it allows you to replicate data and log the replicated updates as well. So if you're updating a database, you typically use Paxos. If you're just replicating information, use atomic multicast. And Cornell built this system, derecho, looking at remote DMA, RDMA. Now we're starting to think, well, if you guys pull it off, we want to look at OAE as well. And derecho turns out to set records in very interesting ways. One is accidentally, by trying to align our versions of these protocols with RDMA's characteristics, we discovered we had built the first optimal implementation of Paxos, a classic sort of protocol family dating back 30 years by now that Leslie Lamport initiated. So at first there was one Paxos protocol that used quorums, but over time 25 Paxos protocols were developed, and we have one too, the derecho Paxos. It's provably equivalent, something called bisimulation, to the standard Paxos, and it's exceptionally fast. It's also, as a performance question, sometimes theory and practice don't align, but as a matter of fact, derecho's performance beats any prior strongly ordered protocol that we could identify. We'd set things up side by side, and it wasn't just RDMA doing it. Even over TCP on normal Ethernet, derecho was faster. And fundamentally, the reason it was able to do this is because it was expressed in terms of asynchronous streams of information. So between any pair of nodes, derecho took the view that there were two connections, one of them for data transfer and one of them for carrying protocol state information, just one between each pair for each type of information. So we didn't have a situation where you have like an unlimited number of connections from A to B, one connection. And that meant that as you learned about protocol state changes, let's say you're A learning about B, you're learning more and more about B's state. You never quite catch up because it's streaming, and you're streaming A state to B at the same time, and it never quite catches up. And then the protocols were defined over these asynchronous streams. We use the term monotonic, meaning that the information you gain just continuously grows and doesn't surprise you with some information about the distant past. Whatever was told in the past is sort of stable, sort of immutable. Now, it turned out that that would not alone be enough to build the atomic protocols we built in derecho. And I had a talk, by the way, on derecho that you could see a recording of. In order to pull it off, we also needed to look closely at the way the RDMA system was talking to memory. And the reason is because you're transferring potentially large objects. Large objects, when you write them to memory these days, are actually written cache line by cache line. A cache line is currently typically 64 bytes. Someday they're going to grow to 128, and I'm sure someday they'll keep doubling beyond that. They correspond to how many wires are on the bus. So Ethernet chiplets also are going to talk to PCIe and other buses at a cache line width. And so RDMA is doing that. And backlogs can arise on the DRAM for individual cache lines. So you can actually have a degree of asynchrony where RDMA tries to write, I don't know, 1K bytes as a series of cache line updates, and they queue up in certain cases. And those particular DRAM cache lines take a little while before the updates reach the memory. And so now the question becomes, if some other party looks at that chunk of memory, what do they see? Well, it turns out you need guarantees in order to be able to prove the properties of your high-level protocol, my atomic multicast. So I'd like to say I multicast to some group of participants and they get all the, but what does it mean to get the message? It ought to mean that if they look at the message, they see the data. And this RDMA property of writing to cache lines, which are asynchronous, doesn't guarantee that by itself. You need a stronger guarantee. You need a guarantee tied to the memory consistency model implemented by the hardware. Now, these days, we talk about those in terms of what are called C and C++ atomics, although in reality, they're implemented by AMD and Intel and other vendors. So Intel will come along and say, this is the instruction set to use when you have an atomic in a cache line. They have to be inside a single cache line each. A cache line is kind of wide, so you can have several variables in there. But the way the hardware talks to memory is always in units of 64 bytes, even if you're only updating some of those bytes. There's a mask. It says this is the portion I'm actually updating. But the operation can be understood as being a cache line wide operation. And that's true for any computer we use today. And C and C++ expose that through a set of types that are called the consistency guarantee types. And one of them is called weak consistency. Another is called release consistency. Weak consistency allows reordering of operations at a cache line granularity. So a set of updates occurring, they can occur in any order. Two different updates can't overlap at the granularity of one cache line. That piece will be hardware atomic at the memory level. There's something called release consistency, which is a stronger guarantee that will preserve FIFO order. And there's atomic consistency, which has all the secret sauce to be able to do things like spin locks that do test and set or compare and swap. Now, RDMA turns out to offer these, but you have to use them through RDMA verbs where you set certain bits. And RDMA also has a way to enable something called memory fencing. A memory fence says, I'd like to have the guarantee that anybody who sees what's going to happen next will also see everything that happened previously. So you have to stabilize asynchronous updates to DRAM before any of the next byte updates become visible. A typical use case might be you put some data into a round robin buffer or something, and you want to be sure it's there before you change the pointer that says how many cells have been filled out. That would be a very representative use of a memory fence. And memory fencing is built into atomic consistency, but you can also ask for it explicitly. And in fact, the hardware has a variety of forms of fencing. Fencing for somebody who's only going to do reads. Fencing for somebody who only did writes and didn't do any reads. And these fences are either automatically generated, or you can explicitly ask for fencing. And these days, the evolution of operating systems like Linux that are heavily concurrent tries to express operations in terms of weak atomics and fencing because it's cheaper than locks. So you can build various kinds of lock-free algorithms. Well, when we built derecho, we had to reason at this level because this is the primitive memory guarantee that RDMA turns out to be offering. And you can pull it off. We were able to build our protocols and establish their correctness that way. So this is just a summary of what I just said before, and I'll just run through it again for anybody who thought that was a little too fast. So these are the consistency properties in the C, C++ standard, which is also the hardware standard. So weak consistency, and you can read about it on Wikipedia. Cache line updates can be reordered by the hardware, but you would never see a mishmash of two cache line updates. So my update, Paul's update, maybe his gets first, maybe mine is first. Maybe I issued two and they come in out of order, believe it or not, that's allowed too. You basically can only use weak consistency if you know you only have one writer. The hardware gets this extra freedom that turns out to make the hardware run faster. The DRAM runs faster. Sequential consistency preserves FIFO ordering from a single writer. Two writers, all bets are off. Atomic consistency, as I said, is very strong. It has memory fencing, and it's strong enough to implement test and swap and set, or compare and swap. And memory fencing is this property that everything that's been done in the past that was asynchronous, we're going to kind of pause until it syncs. Okay, like F-sync to a disk. Now, what about failures, right? I mean, they can happen. The philosophy that we have to think in terms of in larger systems is the idea that the larger system just sails on even though some component has crashed. Now, sometimes on, for example, on the discussions that occur on WhatsApp, which often include people who don't have much background in this, you sort of see confusion around this because they've heard about a famous result from Nancy Lynch called the Fisher-Lynch and Patterson impossibility result. And they prove the impossibility of fault-tolerant anything. They call it fault-tolerant consensus, but every property I mentioned for atomicity includes a consensus aspect. So they basically say, if you got a failure, you can't achieve. But what do they mean? They turn out to mean that no solution that you could build is able to guarantee correctness and progress against all possible patterns of asynchronous failure under an assumption that a failure is an actual, guaranteeable, recognizable, God-given thing, and we're never allowed to get failure diagnosis wrong. We have to wait for this machine if the link to the machine is down, but the machine is up. This is the fundamental FLP problem, that you can't recognize whether the machine is up or the link is down, but FLP requires you to distinguish those cases, and you often have to wait as a result. If we don't care about that, if we want the 500,000 computers in the data center to keep running, and if this machine's link is down because someone stumbled over a cable, or if the machine just went up in smoke, as in this image, we're just going to write it off for the moment. And that's, of course, what data centers do. Nobody has a whole data center wait for one machine. FLP doesn't apply anymore. FLP isn't really the right policy to think about in a system where there's a huge majority and some rack loses its air conditioner and crashes. In that situation, we want to shut the rack down, even if some of the computers are complaining, hey, I'm not really faulty. All right, nearly dead Ned, you remember that from the Monty Python and the Holy Grail? You can whack him on the head. That's what they do in that movie. That's what we can do to evade FLP. So we want the ship to sail on. And what that sort of says is we want a minimal set of properties from Open Atomic Ethernet to enable our stronger atomicity protocols to move forward. Now, one of that set of minimal guarantees is clarity around the memory update policy, just like RDMA had, but perhaps not RDMA verbs. What are RDMA verbs? You speak to the RDMA InfiniBand technology through a really bizarre hardware interface called verbs. No one knows why it was ever called verbs. And everyone hates verbs, so we don't have to go that path. But the aspect that RDMA makes explicit formal properties about how memory is updated and how you can control it, we need that. Well, another thing we need at the basic level is, to the extent that the hardware can help with link integrity semantics is very valuable. What do I mean by that? Well, I have a connection from me to Adrian on some data center. I'm one machine, he's another machine. If that link definitely has gone down in hardware, it's quite useful to have a notification occur to the drivers of the respective machines. And in fact, we ought to sever all the connections. Why do we do that? So you don't get some inconsistency where some things believe there's connectivity and others have lost connectivity. I'm not really talking about connections at an application layer. I'm really talking about connections at the server-to-server hardware layer. Okay, so rapidly discovering discoverable hardware problems and reporting them and breaking any link that has the same connectivity, meaning for Ethernet, probably any TCP session, is quite valuable for achieving a type of agreement on what just occurred. And you get confusion of the type that the FLP proof centered on when you have ambiguity. Just somebody thinks there's a timeout, someone else doesn't think there's a timeout. Adrian is still talking to me, but Paul thinks I'm unavailable. That type of confusion leads to the FLP impossibility. If the system suddenly went dead, it severed all the connectivity between everyone and me, or at least between Adrian and me. That type of clarity, combined with the type of guarantees that you get from knowing which atomics we're dealing with or controlling them, can enable ultra-fast atomicity. So that leads to a view, which is that just as chiplets are designed using TTL, register transfer languages and other kinds of guarantees that we typically formalize and verify, we ought to be thinking in terms of a formal semantic for memory and failure behaviors of open atomic Ethernet. That semantic ought to be strong enough that we can implement higher level things. Derecho is one, but I want to implement all of those different things. I want to implement exactly once RPCs. I want to implement database transactions, all of them. All right. Building those kinds of things efficiently argues for asynchrony and argues for, nonetheless, a strong statement about what that asynchronous thing did. And it argues for notifications and this type of cut the link if anything went wrong on either side connectivity property. And that gives you the fastest responsiveness possible. That is how we were led in Derecho to the world's first optimal Paxos. Not that anyone really cares, but it was interesting that after like 35 years of people doing Paxos protocols, we end up with the first one, not because we set out to build an optimal protocol, but because we were led to it by RDMA happening to have those properties. So we want OAE to have a formal set of properties and to write the formalism down, have a specification. And then that can be amplified into much stronger things like atomicity and agreement on membership and agreement on who's the leader and on ranking. All of these fall into this world of consistency and atomicity guarantees. Higher level stuff enabled by lower level stuff. We can formalize the semantics in various ways. One that I would point people to is Annie Lou's dist-alg work from Stony Brook. She and her husband, Scott Stoller, did this work. Or one of the Coq formalisms. And in that area, I would point to the verified software tool chain from Andrew Appel's group at Princeton. And these are just two examples. You could settle on a different formalism, whatever it is you'd like OAE to actually literally be a chiplet plus a formalism for how it behaves. And these formalisms then enable us to write out our protocols and machine verify them. So there is a dist-alg formalism for derecho, and with Annie's help, we even identified some errors, and we fixed them. Her verifier was able to do that. With distributed Coq formalisms, we can go much further, and we can prove very elaborate distributed algorithms and protocols, things like membership algorithms, and we can prove them correct and formally verify the proofs. So these higher level proofs build on lower level proofs. And what I'm saying in the last box down here is that if I have a system like derecho with a proved correct atomic multicast, I can actually give you the specification of derecho in the same higher level formalism, and you can build on that. And you're building on a strong foundation. And this becomes a selling point, which someday a person marketing the OAE chiplet might find extremely valuable. Be able to say, well, build on any old thing if you want, but if you buy from us, you get these very strong guarantees, which are formally specified in which you can use tools. So let me wrap up and just sort of say that OAE needs to compete with the world's fastest option, which right now is RDMA. RDMA is a stovepipe owned by NVIDIA. You don't want to just adopt RDMA, and you certainly don't want RDMA verbs, which everyone hates, and that's a selling point for Ethernet. So we want Open Atomic Ethernet to be as fast as RDMA, but we also want it, like RDMA, to offer the necessary enablers for atomicity through minimal mechanisms combined with the necessary formalisms to allow people to reason in a rigorous way. Then they'll move the actual logic of whatever they're trying to build into the device driver or into a daemon that might run on Linux or something. That's fine. That's their job. But our job at the level of OAE, and I really should say your job, because as I said, I'm the consultant, others on this call are going to carry this out, is to ensure that what you're building has this degree of basic strength. So I'm going to stop with that. Paul asked me to keep this short and to linger on my last bullet point slide, which he said would then be the spring point for discussion. So let's see what people have to say.
All right, thank you, Ken, for that excellent and very clear presentation. So there are a couple in the chat, one from Adrian and one from Alan. So let's take those first, and then we'll open the floor for everyone else. So Adrian, your question was, is this basically escalate a large category of unknown failures to a single well-understood failure?
So Adrian, what I'm looking for here is probably more minimal than I think what you're asking about, but I understand where you're going with that, and it's a very good question. I think at a higher level, that's exactly what we want, and that different higher level models like transactions for databases or like state machine replication elevate low-level things to different higher-level functionality. But no, I think that for the hardware, the real goal is to say the hardware is capable of detecting a loss of connectivity, at least if we're talking about optical hardware in data centers. And we should do so in a consistent way and report it promptly. So that's really all I'm suggesting. And that if there's any connectivity issue between machine A and machine B, the hardware should signal this in such a way that the device driver, if it wishes to, should be able to instantaneously sever all communication between A and B, and then push that up for higher level. It can be optional, though, and it probably has to be. There are existing TCP systems which would be upset if a connection was unnecessarily broken. So I think things that want stronger consistency would want to enable that kind of severing of connections, and things that don't should get the old default behavior, which is a pain to recover from and has these FLP issues. I hope that answers your question. Is that okay, Adrian? I mean, does that make sense to you?
That's good.
Yeah,
Alan?
I think so. You were talking, one of your examples was about, if you get a failure in a piece of hardware, you can sort of nuke the rack or nuke the machine or something like that. And that was kind of where that thought came from, right? And then
Yeah, yeah.
this whole sort of thing, well, I can't understand all the things that can go wrong. So you have sort of analysis paralysis, but it says, if I can draw a box around it and ignore it, then if
Yeah,
I can
and
box
if I'm
it off,
building your
then I can move on without having to know exactly what went wrong. I just need to know this thing isn't behaving correctly in some way, right?
Yeah, no, sorry for violating Paul's second rule. I shouldn't have interrupted you. Yeah, exactly right. And if I'm building air traffic control, I want to cut things off. I don't want the controller continuing to think they're talking to the plane. I want to give control over to some other air traffic controller, and I want the original controller to realize they've lost connectivity. If I'm building, I don't know, a real-time robot, I might not want that behavior, and I might prefer the old Ethernet characteristic that some things can work, some things don't. And so it ought to be selectively enabled. But there have been systems, there have been papers on systems which literally pulled the power on a rack in a data center in order to force perceived errors to be hard failures. And they showed that it simplified all sorts of things. So in settings where that's the kind of semantic I want, I ought to be able to do it.
Yeah, I did copy screenshots of your slides into the Miro board and write some notes about what you were saying along them. If people
Yeah,
want to.
I'll share those slides. I'm happy to.
There was some of the commentary edit. Anyway, I was sort of editorializing a little
Yeah,
bit.
yeah. Who do I share them to? We'll do that offline, but I'll provide the slides to Paul. I didn't ahead of time because I made them up this morning, and then they can be forwarded to wherever it all belongs.
All
Nothing
right, so
proprietary in this; it's open.
it's
Just
9:52 right now. So we have a question from Alan. Alan, do you want to speak your question aloud?
Yeah. So there are two kinds of failures. One is loud, where the other side knows that the link is dead. Maybe the card failed, but it sent some sort of a signal. But there are also silent failures where it's just non-responsive. And now you need heuristics. And anytime you need heuristics, you're in trouble. So I don't know what the best solution is. What we did was, if one side decides the link is dead, it declares it's dead and requires a restart handshake before it'll talk on that link again. That was the best we could come up with.
Okay,
Yeah, that's very much in line with what I'm suggesting, at least for those use cases that want strong semantics. And again, for those that don't care, we need to support the old defaults.
okay, Hisham, then John Lockwood, and then Harry. Hisham, go ahead with the question.
I thank you very much, Ken, for excellent presentation as usual. But you mentioned Professor in Princeton, Andrew. So I am sort of aware of what he is doing, but maybe if you can elaborate more on how his work in code verification can help this group.
Sure. I'm
More
fortunate.
elaboration, more elaboration. That's
Yeah,
it.
yes, of course. I'm very lucky. However, I happen not to be at Cornell this month and next month, but Andrew is. So Andrew has been starting during COVID, has been spending a lot of time not at Princeton but at Cornell, and over lunches I've learned a tremendous amount about the verified software toolchain. What he did was to first to push Coq towards proofs of C compilers and things like that, but beyond that, towards proofs of distributed protocols. And so VST has been used, it is a Coq. Think of Coq as the underlying language, and then it's kind of like a Coq domain-specific language. I'll call it extension, but it's a fully over Coq, aimed at verifying concurrent programs that exchange messages. And they've done some fairly elaborate things with that. In fact, when he was visiting, we started a project to look at using VST to verify derecho, but we could not convince the NSF that this was a wise investment. And so that hasn't actually been done. But VST is quite a promising cock dialect for doing that type of thing. And I would love to do it if somebody would pay a grad student to work on it.
Okay, we've got a couple of people, Mike. So John Lockwood, you're next, then Harry Quackenbosch, then Bijan, and then Edmund, in that order. Go ahead.
So I posted a message on the chat, but about CXL. And so CXL also is a chiplet protocol. It's going to be widely adopted by AMD, Intel, Qualcomm, ARM, and be used on chiplets, regardless of what we do here, right? Is that, and it has mechanisms for memory semantics and coherency. And so there may be some overlap between what we're looking at with this and what we're looking at with CXL. And I would propose that we could be, the Ethernet part of the chiplet could be much, we probably don't want a lot of overlap, is that there may need to be some, but we kind of, if we could allow the Ethernet to implement what Ethernet will do best, which might be more related to message passing, and let CXL do what maybe it's better at, which is cache coherency. But I'm just curious what the rest of the group feels about this, because I have no stake in the game for CXL. But I'm just kind of bringing the elephant to the table that, at least on chiplets, most chiplets will have a CXL interface, and we probably don't want to have too much overlap between the functionality of the Ethernet and the CXL. So, thoughts?
I mean, I've looked at CXL a fair amount, and it's based on PCI 6 as the transport, and it's a large packet, like 266 bytes. FLIT, it's called, basically. So what you're transferring around a CXL system is these 266 byte FLITs, which are transferring around over basically the same, the hardware layer is the same as PCI 6. So it's not, I don't think it's a chiplet thing. It's really something the CPUs need to implement because they're managing the concurrency, right? And so the chipsets that do memory interface and network that do IO interface, they have modes where the same pins can be used for PCI, and then you can change mode on that and have it. There's a protocol which flips that interface out of PCI into CXL mode. So I don't think it's being used between chiplets. I think it's being used more at system level. That's what I've seen. I'm not sure if that helps clarify, but certainly it's a way of getting fairly large, fairly wide area memory coherency as a goal. So there's certainly something to learn from it.
So Harry, you're next, and then Bijan, and then Edmund.
I'll try to make this really brief. Adrian just triggered a thought. Adrian, the UCIe is it's got a bunch of momentum around chip interconnect. I would have guessed that kind of leads to CXL as a protocol between chiplets, but
UCIe is a different thing from the chiplet, from CXL. They're operating at different sort of layers really in the system, I think.
But isn't UCIe basically PCIe adapted for short distances and low power?
Maybe I haven't looked enough at UCIe, but CXL is definitely more of a long. CXL is designed to go a meter or two.
Okay, my impression was because the UCIe is very similar to PCIe, that would naturally lead to the other thing. But kind of back to my very point. Kind of interesting comments. What do you think about the possibility of doing better than RDMA rather than saying we want to be as good as RDMA? And what implications should the team factor in terms of how it makes decisions about navigating what it's trying to do here?
Sure. Let me say that despite hating verbs, I'm a fan of RDMA. I mean, derecho is certainly fast. I talk a lot to Microsoft. They use RDMA for everything. There are a lot of issues with RDMA, though. It has major security concerns. It would be nice to be able to offer much stronger statements about security, because here with RDMA, you have the end user, whatever application, certainly untrusted, happens to be allowed to generate these Q pairs and construct RDMA instructions, talking directly to the hardware and potentially hosing the hardware. So I think you want the speed to be, fully competitive. You also would like a stronger security statement, because if I take Microsoft as the example, I had a conversation with the data center networking owner, Dave Maltz, and he said RDMA in the current form will never be available to end users, not from him, not from any major company. He said we all have to virtualize it in one way or another because we simply can't trust users to that degree. So you want the full speed to be available, but without that loss of security. So that'd be one point. I think another would be one of my colleagues works on very low layer networking. She's interested in layer 1, layer 2 networking, and what can be done with direct control over optical bandwidths and so forth. Her name is Rachi Singh. It'd be very nice to be able to start to think in terms of the host as controlling data paths, which aren't necessarily originating or terminating in that same host, but in a secure way. Because there are many situations where we would like to do things like move data from GPU to GPU without going through host memory. And probably that's going to become more elaborated over time. So there'll be GPU through an FPGA into a GPU or through some other type of bespoke accelerators. And I think that if chiplet were to, if OAE at least were to pursue some of those opportunities, they'd really be genuine sort of next stage performance opportunities that could offer quite a competitive advantage compared to existing RDMA. However, NVIDIA is evolving RDMA day by day. So I wouldn't count on necessarily maintaining an advantage over them for long. But that's where I would focus.
Bijan, and then Edmund. Bijan, go ahead.
I'm not going to address my comment. It is what it is, but I wanted to respond to some questions about UCIe and such. We have a UCIe effort at the ODSA, which is under server. There's a chiplet work stream and project, sub-project, sorry. And yeah, so the other thing that came up was PCIe and CXL. We also have a very big CXL community that's also in the server group. That's what they call the CMS, or the composable memory systems at this point, but they're focused on CXL. Lastly, I want to point out that the differences between these and Ethernet are that, the PCIe and UCIe, even though they're related in name, they're significantly different. And what's driving them is the reach, which I think somebody mentioned. So the reaches are driving, a lot of different choices as far as, modulation and, error correction and things like that. So where Ethernet overlaps all of this is that, I have been working with other organizations, and we are looking at upgrading the speed of Ethernet. And what comes out of it there might be some opportunities if you look at just logically, not with any specific market point of view, but just logically, there might be some opportunities to utilize Ethernet in the very short reach instead of UCIe, if you can start considering, beachfront problems. And so if you can serialize fast enough, like, SerDes is moving towards 448 gig right now. If you could serialize fast enough, then Ethernet might be an attractive option because of its inherent flexibility. So I'm not advocating this as a use case. I'm just saying that there's some logical overlap in the potential to use it in such a way and the use cases for UCIe. But I do think that UA-Link wants to use Ethernet versus PCIe in the future. I don't think that's a secret. I think they've shared that. But anyway, I'll stop there because time's running out.